So welcome to a new video. So in this video we're gonna see about IO designing, especially 8255. Before we begin, as usual, you want to cover a little bit on what we did or what we need. Okay. Before that, if you need extra info or note on 8255 on how to control it using assembly language, how to program it, watch the previous video, because this one is strictly on designing the hardware interface. Okay, now the stuff that you need to remember is port A 00, port B 01, port C 10, control is 11. So what we're gonna do is in the base address we're gonna plus this. So this is in the binary and this is in the hex format. So for example, if your base address is 80H, so your port A will be 80H, your port B will be 81, your port C will be 82, and your control will be 83. So where does this helps? This helps in the design, and I'll show the design in quite a time. Now another thing that you need to remember is NAND gate. So in NAND gate, if all are 1, the output is 0. Okay, if all are 1, the output is 0. So we will be using NAND gate, so you need to know NAND gate. So all input is 1 equivalent to 0. And is this table needed? Not so, but your IO need to be 1 in order for us to access the input output. So you need to know this, and in the previous lecture I said that I'll show this table somewhere in this lecture series. So this is the selection and IO stuff, but we won't be using much, but if you want you can refer to this specific video. Now our 8085 pin is something like a IC that has so many legs, but this is the block diagram. So we have internal 0 to 7 input, then we have output for port A, port C up, port C down, port B, then we have read, we have write, we have the A1 AO, which is for the control, okay, which is for the control, and then we have reset, we have a chip select, which we will be using with the NAND gate here, then we have the VCC and ground. Okay, this is ground. So these are the expanded node on the list, and this is the picture. Okay, this is the picture of the stuff. Now here we are using a decoder, but in the real case we won't be using decoder. So technically for control we will be using A0 and 1. This is for control, and for chip select, as I said, we will be using decoder, but in this specific case we won't be using this decoder because generically we have G1 and this stuff. So students need to be able to identify in the basic circuit. So this is the generic format, everyone can use it using a decoder sheet. But in order not to be giving student, because this one, if you notice here, if your address is 10100000, is it this is 1, so you should be opening this. 5 is 0 1 2 3 4 5 5. So 7 this here. Correct lah. Now this is equivalent to 8 9 A0H. So for A1H, A2H, A3H. So your address is starting from AO, you use this table, so you use here, you decode it Y1. If it was in 1001 9A, you could have connected it to Y0. So this is quite simple, we don't like simple stuff, so we made it harder. Now you use this specific diagram to make it easy, but it depends on the question as well. Now let us see the question itself. A microprocessor system, 2 PPI, okay, and 6, we don't need the 6 port, 2 PPI. Now PPI 1 is 84H, PPI 2 is 88H. So we need to draw. Okay, you need to draw. Regarding the programming, I have explained it in the previous lecture, so I believe you guys can watch the previous lecture, especially for 8255 programming. Okay, this is for designing, again I repeat. Now this is the circuit they have given us, okay, gave us. The first thing that we need to know is we have two PPI, so we name it PPI1, which is equivalent to AT for H. Immediately we know that AT for H is for A, AT5H is for B, AT6H is for C, AT7H is for control. Now this is PPI1. Then we have PPI2. PPI2 is said to be 88H. Immediately you know that 89H is for A, 80AH is for B, 80BH is for C. Control, sorry, A, B, C control. Now, again, this is in hexa, so immediately after 9 it will be A. Please beware. If we expand this in binary, what we will get? 1 0 0 0. As usual, we separated in nibble 4 4. It would be easy. So this one you will get 0 1 0 0 1 0 0 0 0 1 0 1 1 0 0 0 0 1 1 0 1 0 0 0 0 1 1 1. If we expand this, we will get 1000 1000 1000 and 1001, 1000 and 1010, 1000 and 1011. Now a strange pattern. If you notice both here, the control word is being controlled by the last two. Okay, before we begin, if we notice here, they have mentioned 2 5 6 9 12 15 16. What are they trying to tell us is this is A0, this is A1, this is A2, this is A3. Okay, so the pin arrangement that they have given in the bits are A7, A8, A7, A6, A5, A4, A3, A2, A1, AO. So strangely, what we can see here is for the control, AO, A1 and AO, A1 is being controlled. So immediately we assign AO, A1 for the chip. Now here strangely we see this is the pin 1, so we name it PPI1 and we name it here PPI2. So in the question they mentioned that unconnected X1 to X10 lines, address decoder and also IO. Now here is the X7, X8 and X9, X10. So X7, X8, X7 goes to A1, X8 goes to AO. Okay, you just connect it to there, which makes it a bit easier. Now here the X9 and X10, X9 go to A1 and X10 go to A0. You just connect it to the connection there. Okay, now for the next part, we are trying to connect the balance. So we know that A0 and A1 has been used, so here we could just, maybe we could use other color, so we remove it, or let me just move it by here. Okay, so we already used A0 and A1. These are the balance that we need to use. In this case we notice that, okay, now A7 of us and A2 of us are always on. Okay, now we also need to know that the balance are always 0. Okay, and then our IO, where's the IO? Our IO or memory should be on. Now we know that if all 1, the output is 0. Okay, the chip select is also 0. So technically, can we use other gates? Yeah, but you need to use so many logic. Now what happen is AND gate, we make it everything as 1, so the output would become 0. Okay, 0. Now here the bubble means it's going through a NOT gate, so 0 going through a NOT gate should be 1. If you imagine using a OR gate means everything should be 1 equals to 1, which is off. So sorry, which is 1, so 1 goes in, it becomes 0. we don't need that. We need, because of CS is here, so here it becomes 0, if here becomes 1, so we need 0 in front to make it 1. Okay, in order to get result 0, we could use NOT gate, we could use NOR gate, but we're using NAND gate. Why? Because every 1 is equivalent to 0, so we need to on everything. Now in this case, A7 is on, A2 is on, but the balance A6, A5, A4, A3 is off. Notice that. And also our IO is always on. Why? Because IO1 is equivalent to read and write. So now we need 2 circuits, so 2 NAND gates. Okay, so the first NAND gate, output is O1 because we want to connect it to PPI1, and the O2 is to PPI2. Now this is O2. Okay, now notice here we are given a static pin, meaning that we could not just take A1 and make it here. No, we need to connect it to here first in order for us to understand the connection here. So what I'm gonna do is I'm gonna connect A7 to X1, which makes us quite easier for the NOT gate to be allocated. Okay, X1, X2, X3, X4, X5, X6. Now that I'm not gonna see A as my NOT gate or AND gate or straight gate, I mean the 1, I'm gonna see the X. So here what we're gonna do is we have mentioned it as such. So they have given number, is it? Yeah. Okay, now so what I'm gonna do is O1, or we'll just make it 6 to O1. Here it's damn, they give it 6 also. 6 to O2, 62 and 61, meaning PPI1 and PPI2. Now we are telling them that this is our connection, right? This is our connection. So just write it. X1 is equivalent to A7, X2 is equivalent to A6, and such. A5, A4, A3, and A2. Now notice here that A7, okay, we are gonna talk in X. Okay, we are gonna talk in X. So we notice that X1 is always high, X6 is always high. Balance are gonna be NOT gate. Now, okay, just see here. X1 is always high, IO is always high, X6 is always high. So the balance are gonna be NOT gate. Why? Because they are low. We're gonna make it high. So these are gonna be X2, X3, X4, X5. So here for the second one, if you notice, X1 is always high, X5 is always high. So X1, IO, X5. The balance are gonna be connected to the NOT gate, and it's gonna be X2, X3, X4, X6. So how are you gonna draw here? Now imagine you have X1, X2, X3, X4, X5, X6, IO. Okay, your NOT gate, first NOT gate. This should be a NOT gate, don't confuse. So the first one is X1, then we have IO, then we had I6, then the balance, just connect it. Now the second NAND gate, same, you had 3 normal line, then you have AND gate. Now the AND gate was connected here, connect it here, then you had X5. The balance, connect it normally. The circuit may be a bit not okay. So now you have your O1 and you have your O2. So the circuit that needed is just this, but you need to mention the pins that you are connecting because you need this. Or else if they ask the normal, I deleted it, nice. If they ask the normal diagram, the diagram I showed in the first stuff, the first one, the diagram was quite similar as such. You need to draw that. Okay, so that's all. You need to understand the NAND gate, you need to understand the expansion. Just remember this, and then you need to understand their base address. Once they given the base address, expand it to 4 places. 84 means 84, 85, 86, 87. So immediately you know that A, B, C and control. Then you expand it to this, you see which bits are changing for the control. You need 1 for the control. So take that control, put it to your this one and play with the rest. Okay, and for selecting what to go to NAND and what to go to control, select the one that's stationary. Don't go and select. For example, if you want to select something for the control and also you want to select everything for the NAND gate, right? See here, these are all static even when this is changing. Okay, this was changing, but these are static because this is the base address. You need this, however you need this, because you see the static address is different between PPI 1 and PPI 2, right? So you need to know the pattern. So that's all. Thank you.